In this tutorial, we will make a program to track an object using camera, Jetson Nano, and Dynamixel servos. As a camera, a usual USB camera or RealSense can be used. The big difference between simple object recognition and tracking is that even when you have several objects of the same class, tracking algorithm will track only a specific object. As we can see, even if the program recognizes the object with the same class it was tracking, the RealSense keeps tracking the object it was tracking previously. Now, let's see the theory. Let's get familiar with several object tracking algorithms. The most basic algorithm is called SORT. SORT stands for Simple Online Real-Time Tracking. It consists of 4 steps. The first step is detection. In this step, an object detector detects objects that are to be tracked. In this tutorial, we are using YOLOv8 as a detector. The second step is estimation. In this step, detections from the current frame are propagated to the next frame. In the next frame we are estimating position of the target using a constant velocity model. The third step is data association. Having the target boundary box and the detected boundary box, a cost matrix is computed as intersection over union distance between each detection, and all predicted bounding boxes from the existing targets. If intersection over union of detection and target is less than a certain threshold value, then that assignment is rejected. The fourth step is creation and deletion of track identities. In this step, creation and deletion of IDs are done. Unique identities are created and destroyed according to the minimum intersection over union value. Tracks are terminated if they are not detected for some number of frames. SORT performs well in terms of tracking precision and accuracy. But SORT algorithm returns tracks with a high number of ID switches and fails in case of occlusion. To overcome this problem, Deepsort algorithm was developed. Deepsort is an algorithm which tracks objects not only based on motion of an object but also based on appearance of the object. So, it can be defined as a 2-branch framework, with an appearance branch and a motion branch. Let's see features of these 2 branches. The deep appearance descriptor is applied to extract appearance features from detections in each frame. It has a feature bank mechanism to store the features of the last 100 frames for each tracklet. As new detections come, the smallest cosine distance between feature bank and feature of detection is computed. The distance is used as the matching cost during the association procedure. In the motion branch, the Kalman filter algorithm is used to predict positions of tracklets in the current frame. It works by a 2-phase process, state prediction and state update. In the state prediction step, it predicts the current state using formulas 1 and 2. In the state update step, the Kalman gain is calculated based on covariance of estimated state pk' and observation noise Rk. Then, the Kalman gain k is used to update the final state, which is represented by formulas 4 and 5. Mahalanobis distance is used to measure the spatiotemporal dissimilarity between motion state of tracklets and incoming detections. Finally, matching cascade algorithm is used to solve the association task as a series of subproblems. This algorithm gives bigger matching priority to more frequently seen objects. Now let's see the system architecture. As an actuator, we are using Dynamixel servos. These servos are commonly used for robots and there is a lot of reference documentation about them. Also, we are using U2D2 as USB communication converter that enables us to control and operate Dynamixel servos. Since U2D2 itself cannot supply power to servos, we are using U2D2 Power Hub as power supplier. Note that we need 12 volts for servos and 5 volts for Jetson Nano. As a camera, RealSense or USB camera can be used. Also, in case you are using a monitor with USB power supply, you should not draw power from Jetson Nano USB port. It may cause overload followed by crash of Jetson Nano. Now let's do the programming. This tutorial is made based on this repository. Thanks to the authors for sharing this great work. To run the program, we will need these packages. In case of Jetson Nano, we will also need some more additional packages, so we will install these libraries manually. Now let's install required packages. Install Python 3 pip. Pip is a package management system used to install and manage software packages written in Python. Upgrade PyYOML library. PyYOML is a full-featured YAML framework for the Python programming language. YAML is a human-readable data serialization language. It is commonly used for configuration files. Next, install TQDM. TQDM is a Python library that allows you to output a smart progress bar by wrapping around any iterable. A TQDM progress bar not only shows you how much time has elapsed, but also shows the estimated time remaining for the iterable. Install Cython. Cython is an optimizing static compiler for both the Python programming language and the extended Cython programming language. Now install NumPy. NumPy is a Python library used for working with arrays. Install libjpeg. Libjpeg is a widely used C library for reading and writing JPEG image files. Install Matplotlib. Matplotlib is a comprehensive library for creating static, animated, and interactive visualizations in Python. Install gfortran. gfortran is the GNU Fortran compiler, which is part of the GNU compiler collection. Install libopenGlass. OpenGlass is an open-source implementation of the basic linear algebra subprograms with many handcrafted optimizations for specific processor types. Install LAPACK. LAPACK is a standard software library for numerical linear algebra. Now we are ready to install SciPy. SciPy is a free Python library used for scientific computing. SciPy contains modules for optimization, linear algebra, integration, interpolation, special functions, FFT, signal and image processing. Install typing extensions. This package enables use of new type system features on older Python versions. Now we are going to install PyTorch. PyTorch will be installed using pip, but for Jetson Nano we need a pip wheel that was built for ARM Arch64 architecture. Go to this page and download PyTorch binary from the list. Here are the commands required to install PyTorch. In this tutorial we will use version 1.8. It seems that the newest PyTorch version working with Python 3.6 is 1.8. Since this example is written for PyTorch 1.8, just copy these lines and execute in the terminal. To make sure that we have all required packages, also execute the second line. We have installed Cython and NumPy previously, so just install PyTorch. Now we are going to install Torch Vision. All you have to do is just to copy and paste commands under the Torch Vision label. Firstly, install required libraries. Clone Torch Vision version 0.9. Note that you have to replace the version strings to actual version number you want to clone. Move to the Torch Vision directory. In this line, build version variable is set to 0.9. By executing this command, Torch Vision build will begin. We have successfully installed Torch Vision. Install Seaborn. Seaborn is a library for making statistical graphics in Python. It is built on top of Matplotlib and closely integrated with Pandas data structures. Now we are going to install libRealSense. Go to this page. Clone this repository. Move to install RealSense SDK directory. Execute build libRealSense shell script with one job. The job option is required to prevent installation process fail due to memory shortage. Basically, the installation of libRealSense is complete, but we need to do some modifications to make it work with Python. As you can see, the program shows that library files should be in this directory. But actually PyRealSense related libraries are in another place. They are in this directory. So, we have to modify the bash rc file. Go to the home directory and open the bash rc file. And modify the last line. Source bash rc file to apply changes immediately. Check whether you can import PyRealSense normally. As you can see, now we can use PyRealSense library. Install psutil. psutil stands for Python System and Process Utilities. It is a cross-platform library for retrieving information on running processes and system utilization in Python. Install IPython. IPython is a command shell for interactive computing in multiple programming languages. Install Sentry SDK. Sentry's Python SDK enables automatic reporting of errors and exceptions as well as identifies performance issues in your application. Install EasyDict. EasyDict allows to access dictionary values as attributes. Install gdown. gdown enable us to download a large file from Google Drive. Install FilterPy. This library provides Kalman filtering and various related optimal and non-optimal filtering software written in Python. Install Top. It is used to calculate max and parameters in model. Install libcanberra GTK. This is the module that takes GUI events like pressing a button from GTK Plus and plays some configured sound. Install Dynamixel SDK. This package provides Dynamixel control functions using packet communication. Now let's see the code. Please download YOLOv8 tracking zip file from Google Drive and extract it to your home directory. In this folder, we have 3 newly created scripts. These scripts are based on this original TrackPy script. Track RealSense Pi and Track Webcam scripts are simplified versions of Track using Servo's Pi script. So, I will explain the Track using Servo's Pi script since it covers all new scripts. Let's see what parts we have added compared to the original TrackPy script. Here, we are importing Dynamixel SDK. In this part, Dynamixel servo setting is done. These settings are different for each servo model. We can check these values on the Robotis.E manual page. For example, for Dynamixel AX12A, servo address for current position will be 36. Here, initial angles of servos are defined. And here servos are moving to their previously defined initial positions. These are parameters for PID control of servos. LoadStream class has 2 new parameters, resize and RealSense. If you are using this code with webcam, the parameters should be as they are set now, and if you are using it with RealSense camera, resize parameter should be false and RealSense parameter should be true. In lines below if statement we are doing tracking. Note that in this code, the camera tracks objects which belong to cat class and has ID 1. In these lines, center coordinates of target boundary box are calculated. Here, error between boundary box center Y coordinate and image center coordinate is calculated. Then, we calculate the angle which servo should move using PID control method. In these lines, we are doing same calculation for X coordinate. In this part, servos are moving to target angles. Now, let us see what modifications we have made to LoadStream class. Definition of this class is located here. Let's open this file. Since we will use RealSense, here we are importing PyRealSense library. Here is a RealSense part of the code. Here, image size, format and frame rate are defined. Pipeline start means that we start pipeline streaming with configuration we set in the above line. The alignment utility performs per pixel geometric transformation based on the depth data. Here, wait until a new set of frames becomes available. The frame set includes time-synchronized frames of each enabled stream in the pipeline. Here we get aligned frames from RGB and depth camera. In this line, a new thread is created to get video frames from RealSense. If the resize parameter is true when we are using a webcam, the image is resized to 640 by 480 image size. Also, we have created 2 functions to update video frames according to whether webcam or RealSense is used. Let's run the code. Firstly, we will run the code only with a web camera. Open the terminal and move to YOLOv8 tracking. Execute the track webcam Pi script using YOLOv8 waits. Now we are going to run the code which works with servos. Note that we should execute the chmod command to enable the program to access the USB port to which servos are connected. Then, execute the track using servos Pi script using YOLOv8 waits.